24 billion kilometers from Earth, a 49-year-old spacecraft is sitting inside a region of space hot enough, by one measure, to vaporize steel instantly, and it is doing so completely unharmed. That region does not appear in the textbook diagrams of the solar system's edge drawn up before Voyager 1 actually got there. Scientists nicknamed it, only half-jokingly, the Wall of Fire. And alongside that discovery sits a second, equally strange finding, a magnetic field that was supposed to change direction sharply at the edge of the sun's influence, and instead, when Voyager 1 actually crossed that boundary, barely changed direction at all. This is the story of what Voyager 1 actually found at the true edge of our solar system, why it does not match what any model predicted going in, and why, despite temperatures that sound genuinely apocalyptic, the spacecraft carrying the instruments that discovered all of it remains, all these years later, completely intact. To understand why this region caught heliophysicists so off guard, you first have to understand exactly what boundary Voyager 1 was crossing when it made these discoveries. Our sun does not simply sit quietly in empty space. It constantly exhales a stream of charged particles called the solar wind, which inflates an enormous, roughly bubble-shaped region around the entire solar system known as the Heliosphere. That bubble extends well past the orbits of every planet, but it is not infinite. Eventually, the outward pressure of the solar wind is matched and overwhelmed by the pressure of the interstellar medium, the thin gas and plasma filling the space between star systems throughout the galaxy. The boundary where that balance tips is called the Heliopause, and on the 25th of August, 2012, Voyager 1 became the first human-made object in history to cross it, leaving the sun's direct influence behind and entering a true interstellar space. For years after that crossing, scientists working with the trickle of data still returning from Voyager 1's aging instruments assumed the region just beyond the heliopause would behave in a relatively predictable way, a fairly calm transition zone separating one environment from the next. What the spacecraft's instruments actually recorded painted a considerably more dramatic picture. Just beyond the heliopause, Voyager 1's data indicated plasma temperatures reaching somewhere in the range of 30,000 to 50,000 Kelvin, a figure that, translated into terms most people can intuitively process, sits in the same general neighborhood as the surface of some stars, dramatically hotter than anything associated with the calm, empty vacuum most people picture when they imagine the space between stars. That number alone is what earned the region its nickname, the Wall of Fire, a boundary layer of superheated plasma sitting right at the edge of our solar system, a feature that simply was not part of the standard picture of the heliopause before Voyager 1 actually measured it directly. And yet, despite sitting inside a region technically hot enough to instantly destroy nearly any material object here on Earth, Voyager 1 has continued operating, its instruments returning data, its systems functioning, without a hint of the kind of damage that temperature would suggest. The explanation for that apparent contradiction comes down to a distinction that turns out to matter enormously once you leave the relatively dense environment of a planetary atmosphere: the difference between temperature and heat. Temperature, in physics, is fundamentally a measure of how fast individual particles are moving. In the W, all of fire region beyond the heliopause, the comparatively small number of particles present are indeed moving extremely fast, fast enough to register that eye-catching 30 to 50,000 Kelvin reading. But heat, in the more practical, everyday sense of energy actually transferring into an object and damaging it, requires those fast-moving particles to physically collide with that object in large enough numbers, frequently enough, to transfer meaningful energy into it. Interstellar space, even in the superheated boundary region, remains an almost unimaginably good vacuum, with particle densities so low that Voyager 1's hull is struck by these fast-moving particles only rarely, nowhere near often enough to transfer damaging amounts of thermal energy into the spacecraft. The plasma is genuinely measurably hot by the physics definition of the term. It simply is not dense enough to burn anything, a distinction that has allowed one of humanity's oldest continuously operating spacecraft to sail directly through a region of space that sounds on the surface like it should have ended the mission instantly. The second major surprise waiting at this boundary struck at something considerably more fundamental to how scientists modeled the heliosphere in the first place, and it involves the region's magnetic field rather than its temperature. Going into Voyager 1's crossing, the prevailing expectation among heliophysicists was that the magnetic field inside the heliosphere, shaped and dragged outward by the sun's own rotating magnetic field embedded in the solar wind, should be oriented in a distinctly different direction from the magnetic field of the surrounding interstellar medium, a field with its own separate origin and orientation, shaped by entirely different processes operating across the wider galaxy. Crossing the heliopause, in that expected picture, should have meant crossing into a region where the magnetic field pointed in a noticeably different direction than it had just moments before, a clean, measurable signature, confirming that the spacecraft had truly left one magnetic environment and entered another. That is not what Voyager 1's magnetometer actually recorded. Instead, researchers found that the magnetic field just beyond the heliopause remained closely aligned with the magnetic field measured just inside it, the orientation barely shifting across a boundary that was supposed to mark a fundamental transition between two entirely separate magnetic systems. That alignment came as a genuine surprise to the researchers analyzing the data, prompting new lines of investigation into exactly why the sun's magnetic influence appears to extend its directional imprint even into the interstellar medium, technically beyond its own bubble, a question that touches on deeper, still unresolved physics involving how the heliosphere's outer boundary actually interacts with the surrounding galactic magnetic field, rather than behaving as the clean, sharp dividing line earlier models had assumed. One proposed explanation involves a process called magnetic reconnection, a well-documented phenomenon in plasma physics in which magnetic field lines from two different colliding magnetic environments can break and reconnect with each other, releasing energy and effectively blending what would otherwise be two separate, independently oriented magnetic systems into something more continuous across the boundary between them. If a version of that process is occurring at the heliopause, dragging and compressing the sun's magnetic field lines as they interact with the interstellar medium's own magnetic field, it could help explain both the observed magnetic alignment and, potentially, some of the elevated temperatures recorded in the same boundary region. Energy transformed from the reorganizing magnetic fields into the heat of the surrounding plasma. That remains an active area of ongoing research rather than a fully settled explanation, but it represents exactly the kind of genuine, physically grounded puzzle solving this discovery has opened up. Researchers are working to update their models based on what the spacecraft actually measured, rather than what earlier theory predicted it should find. It is worth being precise here about what these findings do and do not represent, because some coverage of Voyager 1's recent data has leaned into language, suggesting the spacecraft encountered something bordering on inexplicable, an unknown energy field, or a structure defying all known categories of physics. That framing overstates what is actually a well-documented, if genuinely surprising, refinement of existing plasma physics and heliophysics, rather than a challenge to physics itself. The wall of fire region's extreme temperatures are fully explained by known physics, once the distinction between temperature and heat and the extraordinarily low particle density of interstellar space are properly accounted for. The unexpected magnetic alignment, similarly, is a genuinely open scientific question actively being investigated using established plasma physics concepts like magnetic reconnection. Not a phenomenon that falls outside the framework of known physical law. What Voyager 1 actually discovered was not a place where physics stops working. It was a place where the specific, detailed behavior of known physical processes turned out to look meaningfully different than the simplified models built before any spacecraft had actually been there to measure it directly. That distinction matters because it reflects something true and important about how frontier science generally advances. Nobody had ever sent working instruments across the Heliopause and out into genuine interstellar space before Voyager 1 did it in 2012, which meant every model of what the boundary should look like was, by necessity, built on theory and indirect observation rather than direct measurement. Direct measurement, once it finally arrived, revealed a boundary considerably more complex, more dynamic, and more scientifically interesting than the simpler picture theory alone had produced. Exactly the outcome that tends to happen whenever a truly novel region of space gets visited by working instruments for the first time. Voyager 1's twin, Voyager 2, which crossed its own version of the heliopause in a different location in 2018, has provided crucial additional context for these findings, offering a second independent data point for comparing plasma density, temperature, and magnetic behavior across the boundary. Having two separate crossings at two different points along the heliopause and 6 years apart has allowed researchers to begin distinguishing which of Voyager 1's specific findings represent a genuine, consistent feature of the heliopause boundary as a whole, and which might reflect something more localized to the specific patch of the boundary Voyager 1 happened to cross. Early comparisons suggest the elevated boundary. High temperatures and general magnetic complexity are likely broad features of the heliopause rather than a one-off anomaly specific to Voyager 1's particular crossing point, though a genuinely complete picture will require considerably more data than two single spacecraft crossings can provide on their own. That is precisely the gap a newer mission launched specifically to build a fuller picture of the same boundary region is now working to fill. NASA's Interstellar Mapping and Acceleration Probe, known as IMAP, launched in 2025 and described by its principal investigator as a significantly upgraded successor to an earlier Heliosphere mapping mission called IBEX, is designed specifically to study the heliosphere's outer boundary at a resolution and sensitivity far beyond what either Voyager spacecraft's aging, decades-old instruments can provide. Where Voyager 1 and Voyager 2 offer two precise but narrowly localized direct measurements of the boundary at the specific points they happened to cross it, IMAP is built to construct a broader, more complete map of the entire heliosphere's outer edge, helping researchers determine whether the wall of Fur E and the strange magnetic alignment Voyager 1 encountered are truly global features of this boundary, or whether the true picture varies considerably depending on exactly where along that vast three-dimensional edge a given measurement happens to be taken. None of this diminishes what Voyager 1 itself accomplished, and continues to accomplish, in a mission now well past its 50th year of design life and closing in on its 50th anniversary since launch. It remains the only spacecraft to have spent this long directly sampling the physical conditions of genuine interstellar space, an environment no theoretical model, however sophisticated, can substitute for actual, instrumented in-place measurement. The wall of fire and the aligned magnetic field are not evidence that physics has broken down at the edge of our solar system. They are evidence of exactly the opposite, that physics, applied carefully and rigorously to genuinely new data from a place no working instrument had ever reached before, is still perfectly capable of explaining what is found there, once scientists take the time to understand it properly, rather than reach for the more dramatic, less accurate explanation first. Voyager 1 did not find a place outside the rules. It found a place where the rules, once actually tested against reality, turned out to be more interesting than anyone had written down in advance. It is worth pausing on just how differently this story would read if Voyager 1's plasma instrument had failed decades ago the way its twins did, because the entire wall of fire H, as it depends on careful engineering. Voyager 1's plasma science instrument, the specific sensor responsible for directly measuring the temperature and density of the charged particles surrounding the spacecraft, stopped working decades before the spacecraft ever reached the Heliopause, a casualty of the same slow, inevitable hardware attrition that has claimed instrument after instrument across both Voyager spacecraft's extended decades in space. Without a functioning plasma instrument of its own, Voyager 1's team has had to rely on a more indirect measurement technique, using the spacecraft's plasm, a wave instrument designed to detect oscillations in the surrounding electron density to infer plasma properties rather than measuring them directly. That indirect method has proven remarkably capable, but it does mean some of the most eye-catching temperature figures associated with the wall of fire have been derived through careful, well-established physics calculations applied to indirect readings rather than a single, simple direct thermometer measurement, a nuance worth understanding for anyone digging into the primary research rather than secondary summaries of it. Voyager 2, whose plasma instrument remained functional through and beyond its own 2018 Heliopause crossing, has actually provided the more direct confirmation of elevated boundary temperatures, offering scientists a genuine instrument-verified data point to compare against Voyager 1's indirectly derived figures. That combination, one spacecraft supplying direct plasma measurements, and the other supplying magnetic field and plasma wave data from a different crossing point entirely, has turned out to be scientifically valuable precisely because of how differently each probe's remaining instrument suite has aged, each one filling in a piece of the picture the other can no longer measure directly. It is a reminder that even significant scientific discoveries at the frontier of human exploration often depend on exactly this kind of improvised patchwork data reconstruction, scientists making the most of whatever instruments happen to still be working on a nearly 50-year-old spacecraft rather than the clean, single instrument confirmation a newly designed mission could provide. That patchwork quality extends to how confident researchers can be about the wall of fire's true extent and permanence. Because Voyager 1 is a single spacecraft moving in a single direction, its data describes conditions along one narrow path through the Heliopause boundary, sampled at one specific window in time, rather than a continuous, ongoing survey of how that boundary might shift and change as the sun's own 11-year activity cycle rises and falls. Solar activity is known to cause the heliosphere itself to expand and contract somewhat over time, meaning the exact conditions Voyager 1 measured at its own crossing may not perfectly represent the boundary's behavior during a different phase of the solar cycle. Another open question that only additional missions, additional crossings, and considerably more data than two aging spacecraft can single-handedly provide will eventually help resolve. Until then, Voyager 1's Wall of Fire stands as one of the most striking, well-earned discoveries in the entire history of solar system exploration. A genuine surprise wrestled carefully back into the framework of known physics, rather than a mystery physics itself has yet to solve. There's a fitting symmetry in how this story closes, one that connects Voyager 1's oldest discoveries to its newest. The spacecraft that first showed humanity close-up images of Jupiter's swirling storms and Saturn's rings in the late 1970s and early 1980s is the same spacecraft now redrawing the map of where our solar system actually ends, using instruments decades past their original design life, patched together through exactly the kind of improvised cross-referenced analysis described here. Every dataset Voyager 1 has returned since crossing the Heliopause in 2012 has arrived slower, fainter, and harder, one than the last, filtered through a communication delay now stretching past 22 hours each way, and pulled from a spacecraft whose power budget forces engineers to choose, deliberately, which remaining instruments are worth keeping alive. That the wall of fire and the aligned magnetic field emerged from data collected under those constraints, rather than from a purpose-built, fully instrumented interstellar probe only makes the discovery more remarkable. A genuine scientific first pulled from hardware that was never expected to still be listening, let alone still teaching us something new. This far past the mission's original 4-year plan to tour the outer planets and call it a career.